bit. So I hope you'll find something that will interest you in this one. And yeah, what I'm talking about is going to be small time estimates for kernels of strictly hypoelliptic diffusion. In fact, I'll concentrate in one specific example of a hypoelliptic diffusion. Let's first of all get you an idea of what I'll be interested in. So here are two examples of a very nice diffusion. So in this case, I have just a Brownian motion in the plane. I just write it maybe in a different way that you're used to, but the idea is that I have in R2, so just in the plane, I have noise in one direction, noise in the other direction, and I have a certain kernel associated to that, the density of the process after a certain time. And this is going to be just obviously, well, if these are constants, this will be a Gaussian. And what I'm interested in is the fact that, in fact, I have around me, I will go to a given direction in more or less a scale square root of t, right? It's going to be square root of t if these two are constant. And the fact is that it's also going to be square root of t if they are non-constant, provided we still have the two that are independent ones. Right here we have another example of a diffusion. In this case, it's the contact case. So imagine you're in R3 this time, and these are planes. So I have, yeah, get your hand. My plane in the middle right here is my hand, and then when I move to the side, I have a plane that twists like so. So around the plane here, it twists, and when I go up, it's going to be the same. So I have the same flat plane here, same flat plane here. And what I'm going to do is add noise. So my Brownian motion or my diffusion starts from a point, and then it gets random kicks only in the direction of the plane. So obviously it can go in this direction, it can go in this direction, but it can also go up, provided it moves a bit. So it has to do like some kind of a loop, has to go this way and then move up along an ellipse of sorts and go back. But that is way more difficult for the diffusion to get there. So in fact, you'll have square root of t in the direction of the plane, and t more or less as a typical scale, like in the third direction. Right? I didn't find an illustration for this, but that's basically what it is. And it works as long as you have that kind of geometry. It does not have to be precisely the description that I tried to give you here. It has to be something that kind of looks like it. If you have two vector fields and the Lie bracket is non-zero everywhere, then it's going to be fine. And the question I want to ask is, if you give me any diffusion, maybe not any, obviously it's I'm going to restrict to a very short, small class of diffusions actually. If you give me like a diffusion that is not one of these two, and in particular, I'm going to be interested in hypoelliptic diffusions. I'm going to tell you what it is in a bit. What can I say about the scalings in the different directions? So elliptic is I have noise in every direction. Subelliptic is I have enough noise to get me everywhere. And subelliptic, and hypoelliptic, strictly hypoelliptic is I don't have enough noise to go everywhere, but if I add some drift, so I have Brownian motions, like Brownian kicks everywhere, but also a drift, and the drift helps me to get everywhere because without the drift, I wouldn't be able to. What can I say about hypoelliptic diffusions? Oh, sorry, the light went down. Yeah, that's basically the idea. The kind of thing I want to say, and specifically, this is the kind of results I'm looking for. So this is the density of a certain process. Obviously, it's gonna explode in time, but I want that in good coordinates. So that's my p check. So my p check, for instance, in the case of the Brownian motion, will be it's p, but that exploded in every direction according to square root of t in where it's square root of t according to t, and then I'll get higher powers of square root of t. So I'm going to explode my p in a good way, and I want that this zoomed in version of my u be nice, right? I want it, so this version right here, to be very nice. And you see that there's no dependency on t right here in this thing. And in fact, the type of methods that I will describe give me an expansion. It's an asymptotic expansion in square root of t. So it's a bit more subtle, but we can see that in many contexts, I can prove that this thing right here converges uniformly and in fact smoothly. So every derivative converges uniformly as k varies. So I'm stacking things in order square root of t. Okay, so that's it for my introduction. So I'm going to do it in 2 steps. First, I'm going to describe more or less the strategy of proof in the elliptic and the contact case, and then I'll get to actually kinetic Brownian motion, which I think gives you a good idea of what's happening in the hypoelliptic case, even if it is very much a very specific example, and I believe that it generalizes. Yeah, it really depends on the situation. Yeah. So the strategy is we will, so I'm thinking about the elliptic case, that would be just a Brownian motion, or the sub-elliptic case, that would be the contact thing when I have my planes. So we start with an equation, and we want to replace the equation, the stochastic equation, right, the SDE, by a simpler one that will be polynomial, or just the Taylor expansion, a clever one, and then show that actually this contributes the main term of my asymptotic. For the simple polynomial, it's kind of anyone's guess. You have to make a guess at some point, and once you do that, to show that it gives lower order term, there's kind of an easy approach, something that it's just a method, and it may not work every way, but in every time, but it's really every time the same thing. You want to show that the approximation you have is well behaved in the scalings you have, right? So if your initial equation you're expecting square root of t, then in your approximate equation you should also have square root of t. You want space-time convolution to behave well, again, with this type of scalings. What does this mean? I'm going to tell you in a bit. And then since u tilde is not, right, that's my approximation. U tilde is my approximation. It's not an actual solution of, it's not the actual kernel, and the actual kernel would be a solution to this equation. This is equal to 0 for L, the generator of the process. So this is not going to be 0. It's going to, but we want it to be small. We want it to be small, and we want it to be small in the language of square root of t, right? And in this scalings. And then what we can do, hopefully, is expand the actual solution. So u is the actual solution as a Duhamel series. So we start with the u tilde, and then we take the convolution by the error. This is my e, forgot to write it, but this is my e, the error. And then we can take the convolution again and again and again and again. And hopefully, since these are going to be more and more regular, hopefully that's the plan, then this series might converge and converge to the actual solution. So in technical terms, what I'm going to do is I'm going to define some nice function spaces. That's my psi A. Psi A is a function space that encodes somehow the scalings in every direction. I want U, as I said, to be well behaved in the with respect to the scalings, which I define as U tilde being in psi 1. I want the convolution, so this is space-time convolution, to behave well in the good scalings. So again, this is what it means for me. And I want the error to be sufficiently nice as well. And if I do that, then if you remember the Duhamel expression, I have U, and then I take the convolution with E, and then I take the convolution with E again. And since I take the convolution with something, then I will add this B every time. So this convolution is going to be psi 1 plus key plus KEs, right? And the more I take convolutions, the higher this is going to be, and this is some kind of regularity exponent. So the more regular the thing will be, right? And so these terms right here are going to be more and more regular, and so hopefully this series will converge. And so I will know that this function right here behaves very well in this scalings, the P check. How does it work on an actual example? So here's the elliptic case. So this has been done for 50 years. But in case, this is how it goes. So suppose you have a Brownian motion on ORD. So I'm assuming that I am in ORD, but also I don't have the standard metric, right? I have a metric on my ORD that is smooth, that is uniformly bounded below. But any kind of metric, I don't require it to be a polynomial or anything. So my Brownian motion locally can be written like this, as some kind of the solution of some kind of SDE. What I'm going to do is take an approximation of this equation, where I just freeze every single of these coefficients at my initial point. Right? So I have a collection actually of approximations freezed at the initial point. And this, in fact, is just diffusion in one direction, one fixed direction, plus diffusion in another fixed direction, etc. So this is just Brownian motion, right? This is standard Brownian motion. Well, standard. It has a covariance, non-zero covariance, well, non-identity. But it is some standard Brownian motion with a given covariance. And so it has an explicit density, and the explicit density is this one. Right? So this gives us immediately the kind of scalings we want to have. I mean, we already knew that we wanted to have, what am I saying? So this thing right here should not be P check, it's P minus P0, that thing right here. But in fact, yeah, once you write in the good coordinates, so this is the time singularity, this is the good coordinates, so you're around P0 and you have some kind of scaling square root of T, then you get some very smooth function, right? It's just a function. It depends on P0 because I'm taking scale product compared to the metric at P0, but still very well, very nice. So U tilde behaves well, right? And what we want to say is that actually the same holds for U, right? And in fact, if you remember, I can actually write a whole expansion of my U. Like, I don't have to stop at my square root of T. I can go as far as I want. I said the idea of proof is just to use Duhamel's formula. I'm just repeating myself, but that's the idea. And so we want the convolutions to be well behaved, and U tilde and the error to be well behaved. And how this works in this particular case, I'm not going to show you, but this is just to give you an idea of what I mean by scaling and what I mean by the solution being nice in a good sense. Yeah, and what I was saying is that actually we want to define good function spaces psi A, and so these conditions have to be satisfied. That's what I was talking about earlier. Right. Hypoelliptic case. So I'm thinking, so it's the case I described just before. You have in R3 your collection of planes, and you have diffusions along these planes. And I'm going to say that I have diffusion in direction X and diffusion in direction Y with two vector fields. If you don't like this, you can add a drift in the direction in the plane to make it more intrinsic, everything. Yeah, anything will work. It's not important. What I do want is that the Lie bracket of the two is non-zero. This is my Z, the Lie bracket. And what it means, again, it means that I can go up, right? If I do my small loop, and then I can go actually against the planes. And now I'm looking for an approximation for my diffusion, right? Because this cannot be solved explicitly, obviously. Well, we don't know anything about X and Y, so it's there's no way we can do anything about it. So what I want to do is consider some Taylor expansion, kind of my solution, of my diffusion. So what I'm going to do is I expand my X around P0. So my X around P0 is expanded. Actually, I just need the derivative of X in the direction of Y, because I just need the Lie bracket in the direction of Z. So I just need the derivative of X in the direction of Y. And I'm just taking the component that actually lands against the plane. Same thing for YZ. Sorry, there's no Z right here. And when I have my Taylor expansion, I just define my approximate solution, approximate diffusion by the same thing. I just expanded my X and Y. Right? I have my X dB, Y dB, have X tilde dB, X tilde, Y tilde dB. And it turns out that actually we have more or less an explicit expression for the density of U tilde. Right? When I say explicit, it's given as a Fourier transform. So there's that, right? There's no, at least okay. Let's say this way, the Fourier transform is explicit. It's it involves hyperbolic tangents, but it's really not that complicated. In fact, it is explicit, and it somewhat does not depend on T, or it depends on T in a very contrived way, well, specific way. If you, so my X and Y were the directions in which I had my diffusion, so I'm expecting to have scaling square root of T in the direction X, square root of T in the direction Y, and then the Lie bracket is my Z, and I'm expecting some T in the direction of Z. So if I actually do this, so I'm starting from P0 and I'm looking at what's happening at scale square root of T in direction X, square root of T in direction Y, T in direction Z, then actually this does not depend on T at all. It will depend on P0 as before, but it does not depend on T. And again, the U is explicit. Well, the Fourier transform of U is explicit, and it's very regular. It is a Schwarz function uniformly in P0 somehow, something like this. And so what we hope, and what is actually true, is that in the same scalings, if we take the actual solution, the one that we did not take the Taylor expansion, we do have the same expression. There's the big O square root of T, but it's still behind as well in the good scalings. And again, if we wanted, we could go higher than this. This is a whole expansion that I can give using the general formula. And how do we show that this is actually close to this? We do the same thing. We define the function spaces psi A, and then under these conditions, we can use the general formula to show that it converges. Okay, so that's the kind of thing, the kind of technique I want to apply to different cases. The cases where I have an actual drift. And the example I'm going to talk about is what I call kinetic Brownian motion. So kinetic Brownian motion was introduced by Schromoka in, I want to say 2005. I might be wrong. 15. She did not actually give it a name, and the kinetic Brownian motion, the name kinetic Brownian motion, I get from Jürgen Angst and Ismail Bayer, who were my advisors at the time. And it looks something like this. So I'm working over R2 in this case. And it was this way: you have the plane, you have a point in your plane, and you are moving along this plane according to a direction. So you're pointing along a certain direction, you're moving following this direction. So this is my position xt, yt. And my direction is given by some angle, right? It's this unit velocity, and the angle is phi t. And I want phi t to be a Brownian motion. So my angle is a Brownian motion, and I'm just following my velocity, that's Brownian motion on the sphere. If you think about it, if you forget about the drift, the Brownian motion is only on the velocity, right? So what it's gonna do, if you just leave it be, is it's gonna turn around the circle, right? Nothing is gonna happen except turning around the circle. So there's no way you can go from one point to another. And in fact, the density would be supported just along a line. Right? If you start from a point, the density is going to be along a line, so it's not going to be smooth, and there's nothing to be said. It's just going to be Gaussian. So you do need the drift to make it hypoelliptic and to get a smooth density. So this thing at any positive t admits a smooth density. So what do I expect about it? So just to say a word about this thing right here. So here I have 0, 0. This is the plane, okay, R2. This is 0, 0. And I'm moving with an initial velocity to the right. I'm moving in this direction. And I'm not moving precisely in this direction, but there's a Brownian motion of the velocity. So in fact, my velocity could go a bit up, a bit down, or it could do something a bit more complicated, right? But most of the time it will go straight ahead, not move too much. And here you just see what's happening for x, y. It's the density with respect to x, y. So the density in phi is hidden. I just integrated over this direction. And you can see that, first of all, this is supposed to be a t right here. Yeah, we're trying to go in this direction in the initial in the direction of the initial velocity. So we should be somewhat concentrated around this point. That said, since the velocity is always of norm 1, we cannot go farther than the ball of radius t. Yeah, in time t, we cannot go out this. So it's 0. So it's a smooth function, but it's 0 all outside this. So this is circled, but actually it's a cylinder, right, of the thing. So we cannot go outside this. It's 0 outside this cylinder. It's still smooth. This should be 0. It's hidden by the image. And what do we expect in terms of scaling? So the phi t is the velocity, right? So I have Brownian motion on the velocity. So this should be square root of t. It's just a Brownian motion. In the direction of y, so if I have my my vector like this, I'm going in this direction, and I have some kind of oscillation, right? Given my Brownian motion, and y is my coordinate in this direction. So it's going to be an integral of something of order square root of t, right? The phi is of order square root of t. I'm taking the integral between 0 and t. So this should be of order t cubed in the direction of y, right? And for x, I'm going straight ahead. So I'm going to have a t, but actually the difference between my t, my actual t and my actual value is going to be, there's a tiny bit of a difference because I'm not precisely equal to 1 in the direction x, there's some kind of small perturbation, and this is t squared, right? Well, it's phi squared. My phi is squared of t. So I'm integrating my phi squared. Phi squared is square root of t squared. I'm integrating this for time t, so this should be t squared, which is my square root of t4. This is what we expect. And it turns out that we can actually prove it. This is how we're going to go. So first of all, I have to, I will rephrase the definition of kinetic Brownian motion. So this should be the solution of some differential equation, well, SDE. My drift is just following the velocity, right? So my velocity is, so the angle of my velocity is phi. So my x moves with intensity cosine phi, my y moves in intensity sine phi. And then I have some Brownian motion along the angle. In fact, there's a Stratonovich differential here, but it could be E2. It's just constant, right? It's just a Brownian motion along a fixed direction. And what we've done before, and what I'm going to do right here again, is we want to find some approximation of this equation, right? So what I'm going to do is I'm going to take the same equation and I'm going to take two approximations of my two vector fields. Right? I'm going to take some Taylor expansion of x, tilde, some Taylor expansion of phi tilde. It just happens that my phi is constant, so I may as well just take phi tilde is equal to phi. But I do want an approximation of x. I'm going to do it this way. So this is my approximate equation that we want. This is my xp. When you take a small variation of angle, you're going to have a small variation in the direction of x. That's going to be of size x squared in this direction. So this is my so this is the actual vector field around p0. And when I take the Taylor expansion, I'm just going to expand this the second order. And this one at first order. So compared to the first two examples, the first one was order 0, the second one was order 1, this one is order 2. Right. And now I have my equation. And it turns out that, so this is the expression for the diffusion. So basically I have, so my x tilde is some quadratic function. This is constant. It turns out that if you look at it, you can get more or less an explicit density for the process. For simplicity, I'm assuming P0 is equal to 0, but you can just make a few, you would have some, I would have some x0 plus, y0 plus, etc. Let's just say P0 is equal to 0. This is the integral of my, this is the approximation of my cosine, and I have something that just depends on my Brownian motion. Same thing, something fairly explicit. And in fact, in the good coordinates, right? So my u tilde t, we're saying that in x, I should be of order t squared in d's. This one should be of order t 3/2, and it is. This is order squared of t. And these coordinates, I'm just the density of this thing right here. Right? So in particular, this does not depend on t. It does not depend on p0. Well, there's no p0 right here, but it's all nice. And in fact, we can show that it is of Schwarz class. It is not obvious, definitely not obvious, but we can show that it is. So my thing right here, for a good scaling, so my p is some function of my p check, given just right here, right, with the good scalings as usual. And it's of Schwarz class. And so I want to show the same thing for my u. Again, plus my square root, which could be expansion. And we are going to do this the same way. I didn't do it before, I'm going to do it right now. I want to define function spaces, right, like so, and conclude using the Duhamel formula. And the function spaces are fairly obvious. it's the functions that behave well in the right coordinates. So these are the right coordinates. So my p right here is given by this. It's the p in the good scalings. I have some time singularity right here. Sorry. Yes. And we want this to be nice enough, and nice enough is a bit heavy, so I didn't write it down. But basically, you want all derivatives with respect to tau, p0, and p to be uniformly bounded. And you want also that when you multiply this by a power of p check, you stay uniformly bounded, so it's Schwarz in this direction. Okay, so as usual, I want to show the three properties, and this time I'm going to give you an idea of how it works. So my u tilde in the right coordinates, I told you, was just a function that depends only on p check, and it is Schwarz in p check. So this function right here is basically u check, and it is well behaved, so that's all good. Step 2 is somewhat difficult. So it's the one that if I take a function that has the right level regularity and another function that has another level regularity, then I'm increasing the regularity when I take the convolution. And it's a bit subtle. So to actually write it down, because the idea is not difficult, you just have to write down the integral. And if you consider this p check not this p star not as p star, but as a p star in the right coordinates around p0, so you have to, there's a dp check, a dp star here, ds. If you consider this the good time of change of variables, then you see that everything is bounded. Again, it's definitely not something I want to show you on a slide, but it works, and you could do it by hand. It's really not that difficult. Step 3, I hope I can give you an idea. So step 3 is I want the error to be nice enough in the good coordinates. So what is my error? Roughly, my error is, so u tilde is solution, is the actual solution, right, of the approximate diffusion. My approximate diffusion has generator L tilde. So the difference between, well, the error I commit is the same thing as just the difference of the operators, or the joint of the operators applied to u. And this is just my x minus its approximation, right? The phi minus approximation is just 0. And everything was done so that it would work, right? And the plan is, when I take the derivative of u in a certain direction, since u in the right coordinates is u check, and I'm gonna get the u check times some time singularity that's coming from the in the good direction, right? So if I have my say my x in this direction, so x is supposed to be of order t squared. Right? This is what I expect my x to be. So if I take the derivative in this direction of u tilde, then I know that the typical scale of oscillations of my function is t squared. So I'm going to have a singularity of t squared. Right? What I'm saying is the derivative of u in this direction x is essentially t squared times the derivative in the right scalings. Right? And in fact, the difference of these two in this direction p0 is big O of phi 4. It's because I took the it's not important, but I took the Taylor expansion of the cosine up to order 2. So order 3 is 0 because it's a cosine, and then I have order 4. And so this is going to be of order tau 4. So I have, well, sorry, of order square root of t 4. And here, oh, sorry, this is not a product. This should be divided by, right? This is this derivative should be way bigger. Should be this divided by this, and so it cancels, right? This one cancels with this one, and so more or less this one contributes something that is already of the order of the thing in the good scale. So it's fine. And you have another derivative, and it works in the exact same way. So E is in psi 1. And so what you can do is you apply the German formula. Again, this one is in psi 1, this one in psi 1, this is one in psi 1, so this is in psi 2. So psi 1, psi 1, psi 1, so you can sum it, and it's in psi 3, psi 4, psi 5, etc. And so since this regularity index increases, in fact, this is going to converge, right? And you can show that it is equal to this sum here. And in this case, you don't even have, it's not an asymptotic expansion, it's really precisely equal to the sum. And so this is the kind of result I was interested in the first place. Yeah, so I kind of lied to you about the fact that I would talk about hypoelliptic diffusions with an S. I talked about one hypoelliptic diffusion, and that was the Kinetic Brownian motion. I'm telling you that it works for different things, and the EIJ is the exact same, but the downside, so it is a very elementary technique, and the downside is that you have to do everything more or less by hand, right? You have to guess what the good scalings are, you have to guess what the good approximation will be, etc. But here are a few cases where you could actually do it. So if you change, so if you remember, I took at the very beginning Brownian motion with respect to any metric, and I said it was close to a fixed Brownian motion with just a freezed metric. And this is true also for kinetic Brownian motion. You can do the exact same thing with a metric that depends on the point, instead of having just Brownian motion on the flat plane. In fact, you can do it in any Riemannian manifold. There's a bit of topology involved here in a higher dimension. But so this one is all right. This one is done. This one I believe should work. Another example would be the Schromoka diffusion. And why do I like this one? It's because, first of all, it's a bit simpler. The equation is a bit simpler. And my hope is that you can actually go one term more. So if you, maybe I should go back a bit. If you go in this expansion, so this one was in psi 1, this one was in psi 1, this one was in psi 1, so this one was in psi 2. And so here in my expansion, my next term is, so I'm starting with T0, so just a constant, and then I have T1, right? But if I do a better approximation here, then this error is going to be smaller. And so this is going to be in psi something bigger. If it's in psi 2, for instance, then this is going to give me a T squared as a first new term. And so I know that everything that contributes at the scale T, not T squared, is going to come only from the term U check 0. And my U check 0 is just if it's just my U tilde. So if I know my U tilde well, if I have a good approximation that I know, and I, for instance, if I sorry, I'll get back to this one. If this one I know very well, and it's a better approximation than just the basic guess, then this is not going to contribute, and I can actually guess the next term in the expansion without having to resort to convolution. So my hope is to that it would be possible to get to the next term in this expansion, in the expansion for the Schromoka diffusion, and the next term will involve derivatives of the metric. It has to, the U tilde, and then hopefully they will be present already in this term in the U tilde, the curvature term, and this one will not interfere with it, so I can actually see that this one will have curvature terms. Yeah, and again, it's kind of a case-by-case technique so far. So I hope also that it would be possible to design more of a systematic way to describe things, but it might be a bit ambitious at this point. In any case, that's more or less what I wanted to talk about today. So thank you very much. Yeah, if you have any questions, please go ahead.
Thank you, Pierre. Does anyone have a question, perhaps? I don't see any in the chat, but yeah. Oh, just a second, Pierre. We need to pass over the microphone.
Yeah,
here it is.
Thank you. Actually, I do know a result for your third direction, the common graph diffusion, right?
Yeah.
Yeah, I know a result from Wang Jing, who is a professor in Purdue University, and she has a paper that is inspired by the common graph diffusion, and her result is about the, the graded large deviation result. So she said that this kind of hypoelliptic diffusion, or more generally, the degenerate diffusions, they could have a behavior of graded large deviation. That is, they could have a large deviation with graded order. I mean, her result is very similar to your result. If you go back to your where you construct the capital psi, right? You have a capital psi.
You want, yeah.
Yeah. A capital. Next page.
Yep.
Yeah. Capital psi. You see in your second items for the capital psi.
Yes.
It do has a graded property, right?
Yeah. Yes.
Yeah. So I think her result is very similar to your result, and your result can also imply something like a graded large deviation result. I think so.
Okay.
Yeah. So yeah. That's what I want to say.
Thank you very much. I was it's somewhat techniques in the in different cases. So in the subelliptic case, but yeah,
okay,
the one in that case. So thank you.
Yeah. In your paper, in your talk, your key example is the kinetic Brownian motion, right?
Yes.
And in her paper, in Wang Jing's paper, her key example is just the common graph diffusion. So yeah, so I think you can check that out.
Yeah. Well, thank you.
Okay. Thank you.
Does anyone have another question? Otherwise, I do. Well, actually, I have two. One is just pure curiosity. The second one is more practical. So I'm well, we don't know each other, but I'm a PDE by training, and I know for a fact that hypoelliptic diffusions lead to some kind of regularization properties for PDEs.
Yes.
Well, in your kinetic Brownian motion, is there any hope that this could, because this, in terms of PDE, if I were to sit down and write a PDE, this would be an extremely degenerate PDE, I guess, right? The law of your process would be would satisfy some kind of parabolic PDE, but very, very degenerate, right?
Well, you can write it down. Can I?
But so is there any hope that it could use your whole machinery to, get refined regularity properties, or?
So you can, so the equation is fairly simple. Oh, sorry, I'm trying. It's a cosine or negative cosine psi in the direction of x. positive, sorry, it's a negative sign, but it doesn't change anything. Phi in the direction of y, and just a gradient. So like this. Right? So so what I'm interested in is the fact that you can prove that this converges like in the small scale, right? If you use the good scaling, this converges to an actual like well-defined limit, right?
So yeah. Oh, so I was wrong. It's actually not that degenerate. I thought it would be much more nasty than the usual. Okay. Oh,
no,
my bad.
so this it's just the fact that you have diffusion in just one direction, and somehow it propagates.
Right. So that's the usual hyperelliptic theory. I mean, in terms of PDEs, that's no more complicated than what people have been doing, right? In the past.
No, it's well, it's still the realms of
I thought because you only had like code dimension 2, or perhaps I thought it would be much more. Okay. And the second one, which is just curiosity. So you're working in finite. So in the first half of your talk, you were working in finite dimensions, and you have like k order scaling for length scales when you need k brackets to generate the missing directions. If you were to be in infinite dimensions, I know Brownian motion is tricky in infinite dimensions, but if you were formally to play this game, and if you needed infinitely many brackets to generate, the missing directions, would you expect exponentially vanishing scales? Something tricky could happen? I don't even know if that really makes sense in infinite dimensions.
Yeah. Okay, so this is not going to be an answer. But here's, I guess, things that people have been interested in doing, let's say. So, I did not. There you go. So say you're interested in this equation, dx 0 t is xt1 dt, dx1 t is x2 t dt, and you go all the way up to xn, say t is a Brownian motion at this point, right?
Yep.
And what's going to happen is you have Brownian motion here, and then the first bracket is going to propagate to xt1 or xn minus 1, and the second bracket is going to propagate to xn minus 2, etc., all the way down to xt0. Okay. So this you need n brackets or n minus 1, something like this, brackets to generate all this. And in fact, if you look at the actual solution of this, this is going to be, so xnt is just Brownian motion, just integrated Brownian motion. Xtn minus 1 is going to be the integral of this, ds. Xtn minus 2 is going to be the integral of this, so the integral between 0 and t of the integral between 0 and s of bs, of bu du ds.
Right.
Etc. And this is more or less a rough path. This is a rough path of degree of a size n of well, associated to the Brownian motion. So I guess, well, so we would call that, I guess, the nth rough path associated with b t. It's not exactly precisely this expression, but you can express it as like a big polynomial in this. And this is an object that's being studied very much. And in fact, it's really interesting as an object when you take the limit, right? When you take this object right here, the infinite rough path, well, when you consider all the iterated integrals, yeah, this has been studied. Can I say anything about it right now? No, I don't remember anything.
Okay, but it's well defined. I mean, the limit exists in some sense, and
in some sense, yeah.
Presumably there should be kind of a remainder of your scaling limits in some sense. No, you should expect to be able to say something, since you're able to, give a detailed description of the length scales when n is fixed.
Yeah.
Yeah, there's hope to say something. No.
What I don't like about it is that you're interested in the density, and the density is defined with respect to something, and I don't know what this something would be. Right.
Right.
You have what you were asking for is a Lebesgue measure in infinite dimension.
Yeah, no, I'm perfectly aware that
And other than that, you'll have like this is purely like this is equal to square root of t b tilde 1, right? And this is just t b tilde, well, integral of b tilde 1 delta s ds between 0 and 1. The scaling is really clear here. You get powers of t, and it's completely homogeneous. The scaling is clear. The object, even the difficulty is already present at fixed time, right? The difficulty is not to go to 0, because then you know the scalings are what you expect: the square root of t, and powers of square root of t.
Okay. All right. Thank you. So if there's no other questions, let's thank Pierre again. Oh, there is one. Oh, sorry. Who? No? Ah, no, sorry. Sorry, Pierre. No, mistake. So let's thank Pierre again, and we will reconvene in half an hour after a short coffee break on our end in Lisbon. Thank you, Pierre.
Thank you.